Time doesn't flow the same for everyone. It actually slows down the faster you move. This mind-bending truth comes from Albert Einstein's theory of relativity, which showed that space and time aren't fixed but flexible, woven together into a single fabric we call spacetime. As an object's speed increases, time itself stretches and slows compared to someone who's standing still. And this isn't just science fiction, it's real, proven by experiments with fast-moving particles, atomic clocks, and even satellites orbiting Earth. And if you've ever wondered how or why this happens, watch this video till the end and subscribe to the channel. Let's begin. In our daily lives, time feels perfectly steady, an ever-present rhythm we can trust. Every second seems identical to the last, each minute unfolding with dependable precision. Whether we're running to catch a bus, lying on the couch, or flying thousands of feet above the ground, a second still feels like a second. Our watches, phones, and clocks tick away in unison, giving us the comforting illusion that time flows evenly for everyone, everywhere. It's so ingrained in our perception that we never question it. We plan our days, our years, even our lives around this unwavering flow. The laws of our routines depend on it. Breakfast at 8, meetings at 10, sunset at 6, all guided by time's supposed constancy. But this feeling of uniform time is only an illusion born from our limited perspective. We move so slowly compared to the cosmic scale of motion that we never notice time's subtle flexibility. In truth, the universe doesn't keep a single clock for all of us. And as we'll soon see, this familiar sense of steady time begins to unravel the faster we move through space. That comforting sense of steady, universal time begins to crumble once we push beyond the slow motions of everyday life. The truth is, our ordinary experience of time's constancy is only approximately correct, a convenient illusion that works because we move so incredibly slowly compared to the speed of light. At the scale of walking, driving, or even flying, the effects of relativity are so minuscule that they're practically invisible. A clock on a speeding jet might tick a few billionths of a second slower than one on the ground, far too small for our senses to detect. But when speeds approach the cosmic limit, the speed of light, roughly 300,000 kilometers per second, everything we think we know about time begins to break down. Our intuition, shaped entirely by life at slow speeds, simply fails us. We expect cause to follow effect in a neat order. We assume time moves the same for everyone, and we believe simultaneity, two events happening at once, is absolute. Yet near light speed, none of that holds true. What seems like 1 second to a stationary observer might stretch into minutes or hours for someone racing close to light speed. The very rhythm of existence bends. It's not that clocks malfunction or perception distorts. Time itself genuinely slows. The closer we move to light speed, the more reality diverges from what our everyday intuition tells us. The universe, it turns out, plays by rules that only reveal themselves when we dare to move fast enough to see them. As our everyday sense of time begins to falter at high speeds, we arrive at one of the most profound insights ever conceived in human thought. The realization that time and space are not separate entities at all, but two inseparable aspects of a single cosmic fabric. This was Einstein's revolutionary leap, the idea that space and time merged together into what he called spacetime. Before Einstein, scientists like Isaac Newton imagined time as an invisible, universal background, a perfectly synchronized clock that ticked away the same for everyone, everywhere. Space, in Newton's view, was a vast, unchanging stage on which the drama of the universe unfolded. But Einstein shattered that centuries-old picture by revealing that the stage and the ticking clock are deeply connected. They can bend, stretch, and warp in response to motion and gravity. This insight emerged from Einstein's simple but world-altering realization. The laws of physics should look the same for everyone, no matter how fast they're moving, and the speed of light, astonishingly, should remain constant for all observers. To make that possible, something else in the universe had to give way. That something was the very structure of space and time themselves. When you move through space, you are inevitably affecting how you move through time. They are two sides of the same cosmic coin. The faster you move through space, the slower you move through time. To understand this more deeply, imagine space-time as a vast, flexible fabric stretching across the universe. Every object, a person, a planet, a star, exists as a kind of path through this fabric, moving not just through space, but through time as well. For most of us, traveling at everyday speeds, our paths through space-time barely warp this fabric at all. But as we move faster, our trajectory through space-time tilts, trading motion through time for motion through space. It's as if you're drawing a diagonal through this four-dimensional grid. The steeper that diagonal becomes, meaning the faster you move through space, the less distance you cover through time. That's why, for someone hurtling close to the speed of light, time literally slows down relative to someone at rest. Einstein's insight didn't just redefine time, it redefined reality itself. What we call space and time are no longer independent. They form a single dynamic continuum that can be stretched and twisted by both motion and mass. Even the ticking of a clock, the beating of a heart, or the decay of a particle depends on how it moves through this continuum. The universe, therefore, is not built upon an absolute framework. It's built upon relationships, relative motion, and geometry. This realization was nothing short of revolutionary because it suggested that the experience of time, something we consider so deeply personal and constant, is actually dependent on our movement through the cosmos. Two observers moving differently through space-time won't agree on how long something takes or even on whether two events happened at the same time. Each of them experiences a unique slice of space-time, a personal version of reality that's equally valid. In this new picture, there is no single universal now. What's now for you might be in the future or the past for someone else moving at a different speed. And yet, this isn't just philosophical speculation. The mathematics of relativity backs it up with astonishing precision, and countless experiments have verified its truth. But perhaps what's most beautiful about Einstein's insight is that it gives us a new way to understand motion itself. When you move faster, you're not just racing through space, you're changing how you experience time. The two are intimately linked, forever bound by the geometry of space-time. This means that your life, your heartbeat, your thoughts, and even the ticking of your watch are all subtly influenced by your motion through this vast cosmic fabric. Einstein showed that we can no longer think of time as something that exists independently of space. It's not an invisible metronome ticking in the background of the universe. Instead, it's a dimension, one that flows differently for different observers depending on how they move. And that understanding would go on to reshape everything from our grasp of gravity to the design of modern technology. By recognizing that motion affects both space and time, Einstein didn't just change physics. He changed our perception of reality. Suddenly, the universe was no longer rigid and absolute. It became dynamic, flexible, and deeply interconnected. And it's this interconnectedness, this inseparability of space and time, that lies at the heart of why time slows down at high speeds. Because if the speed of light must remain constant for all observers, then the universe must adjust something to make that possible. And as we'll soon see, what it adjusts is time itself. At the center of Einstein's great revelation lies one of the most extraordinary facts in all of physics. The speed of light is constant, absolutely, unshakably constant. No matter who you are, where you are, or how fast you're moving, light will always travel at the same speed, about 300,000 kilometers per second, or roughly 186,000 miles per second. It's the ultimate speed limit of the universe, a cosmic boundary that nothing with mass can ever cross. This constancy is not just a curious quirk of nature, it's a foundational rule that governs the structure of reality itself. Before Einstein, scientists believed that light, like sound or waves on water, must travel through some medium, something they called the luminiferous ether. They imagined that if you moved toward a light beam, you'd measure it going faster, and if you moved away from it, you'd measure it going slower, just like how the sound of a passing car changes pitch because of motion. But in 1887, the famous Michelson-Morley experiment shattered that assumption. No matter how they measured it, light speed refused to change. Whether the Earth moved toward or away from a beam of light, the speed remained exactly the same. It was as if the universe itself refused to let light speed vary for anyone. When Einstein began to think deeply about this puzzle, he took a radical step that no one else had dared. He accepted the constancy of light speed as a universal truth, not an exception, but a principle. From that one bold idea, the rest of relativity followed almost like poetry. If the speed of light is the same for everyone, then space and time cannot be absolute. Something else must shift to make this constancy possible. That something, as Einstein realized, was the very fabric of reality. Space and time themselves would have to bend, stretch, and adjust so that light could always move at the same unchanging pace. To see how strange this really is, imagine two people observing the same beam of light. One is standing still, and the other is zooming through space at half the speed of light. Intuition might tell us that the moving person should see the light racing ahead at a slower relative speed, perhaps only half as fast. But no, both observers, no matter their motion, will measure the beam traveling at exactly the same speed, 300,000 kilometers per second. That's not just remarkable, it's deeply counterintuitive. It means that our basic concepts of time and distance must be wrong. To preserve the constancy of light, the universe adjusts time and space in ways that defy common sense. For the moving observer, time slows down and distances contract, balancing the equation so perfectly that light speed never wavers. This constant speed of light is more than just a number. It's a cosmic principle that defines the ultimate speed limit for everything in existence. No particle, signal, or piece of information can exceed it. The closer something gets to light speed, the more energy it takes to accelerate further, and the more its perception of time slows down relative to everything else. Approaching light speed doesn't just make you fast, it reshapes your entire experience of the universe. For something traveling at light speed, time itself stops completely. There is no before or after, no past or future, only an eternal present. And what's truly breathtaking is that this rule applies universally. Whether you're on Earth, orbiting a distant star, or speeding through intergalactic space, you'll always measure the same speed for light. It's as if the cosmos has one unbreakable law written into its very structure. Light is constant, and all else must bend to accommodate it. That constancy is what forces the rest of physics to adapt. To make light speed unchanging for everyone, the universe must stretch and warp time and space to compensate for motion. When you move faster, time slows down for you. When you move slower, it speeds back up, all to keep light speed perfectly balanced for all observers. It's not that light changes, it's that you do. This realization forever altered our understanding of motion and reality. It told us that the universe does not revolve around our human intuitions. Instead, it obeys a deeper, more elegant logic, one where time and space are flexible, dynamic quantities that yield to a single, universal constant, the speed of light. And as we'll soon see, This constancy of light is precisely why time slows down at high speeds. Because in order for that cosmic speed limit to remain fixed, something fundamental in our experience of time must give way. The constancy of the speed of light may seem like a simple statement, but hidden within it is one of the most profound consequences in all of science, the realization that if light speed can never change, then the universe must adjust something else to make that possible. And the thing that adjusts is time itself. This is the heart of Einstein's insight. The speed of light remains constant for everyone, but to keep that true, time must bend, stretch, and slow down depending on how you move. Let's unpack why this has to happen. Imagine two people watching the same beam of light. One stands still, and the other races alongside it in a spaceship moving at an enormous fraction of light speed. According to common sense, the person on the ship should see the light moving slower. After all, they're chasing it. But the universe doesn't work that way. Both observers measure light speed as exactly the same, 300,000 kilometers per second. No more, no less. How can that be? The only way to keep that equality is if time and space themselves stretch or compress differently for each observer. Think of it like a cosmic balancing act. The universe is committed to one unbreakable rule. Light speed never changes. So something else must flex to preserve that rule. When you move faster, distances in the direction of motion become shorter, a phenomenon called length contraction, and time itself slows down, time dilation. The faster you go, the more extreme these effects become. From your perspective, nothing feels different. Your heart beats normally, your clock ticks as usual. But to someone watching you from a stationary position, everything you do appears to happen in slow motion. The seconds between your heartbeats stretch out, your clock ticks slower, your very passage through time is gentler than theirs. This interplay between speed, space, and time is not a quirk. It's the deep geometry of the universe at work. Space and time exist in a kind of partnership, and the total motion through space-time must always balance out. You can think of it this way. Every object in the universe is always moving through space-time at the same combined rate, the speed of light. But that motion can be distributed differently. If you're standing still in space, you're moving entirely through time. If you start moving through space faster, then your motion through time must slow down to keep the total constant. That's why, as your speed increases, you experience less passage of time compared to someone at rest. The universe ensures that no matter how fast you go, you never exceed the speed of light, because as your motion through space grows, your motion through time diminishes in perfect compensation. To see this more clearly, think of space-time as a kind of cosmic grid. For someone standing still, their path through the grid runs almost entirely upward, representing steady progress through time, but little movement through space. For someone speeding close to light, their path tilts sharply, cutting diagonally across space and time. The steeper the angle, the slower their progress through time. At light speed itself, the path becomes perfectly horizontal, all motion through space, none through time. That's why, for a photon, the particle of light, time doesn't flow at all. From light's perspective, it never ages, never experiences distance, and never moves from then to now. Every photon is, in a sense, frozen in eternal motion, existing everywhere along its path at once. This perspective may seem abstract, but it reveals something astonishing about reality. Time isn't an independent, fixed background. It's a variable shaped by motion. The universe preserves the constancy of light by allowing time and space to stretch in just the right way to make all observers agree. This isn't just mathematical trickery. It's been confirmed over and over through experiment. When scientists send precise atomic clocks on jets circling Earth, they return slightly behind their twins on the ground. When subatomic particles called muons race through Earth's atmosphere at near-light speeds, they survive longer than they should because their internal clocks run slower. In every case, the universe enforces its rule. Light's speed stays the same, and time bends to make it so. What's truly elegant is how simple this all becomes when viewed through the lens of spacetime. Light's constancy is like a thread woven through the very structure of the universe, and everything else, time, space, motion, even gravity, adjusts itself to preserve that thread. The closer we move to that ultimate limit, the more the fabric of time stretches. Seconds grow longer, distances contract, and the familiar order of reality starts to shift. It's as though time itself is a currency that must be spent differently depending on how much motion through space we use. So, when we say that time slows down at high speeds, what we really mean is that the universe is keeping its perfect balance. Light refuses to change speed. It's the one unwavering law, and in return, time yields. Every tick of the clock, every beat of the heart, every fleeting moment of life becomes elastic, bending gently under the weight of motion. The constancy of light doesn't just shape physics, it shapes existence itself, dictating how we move, how we age, and even how we perceive the flow of reality. And from this profound relationship between speed, light, and time emerges one of the most remarkable effects in all of relativity. Time dilation, the phenomenon where time itself slows down for objects in motion. It's not an illusion, not a trick of perception, but a fundamental truth of the universe. And understanding that is the key to grasping how motion through space can so deeply alter our journey through time. From this cosmic balancing act between motion, space, and time emerges one of the most astonishing realities in all of physics: time dilation. Time dilation is the name we give to the phenomenon where time itself runs more slowly for an object in motion compared to one that's stationary. In other words, if two observers are moving relative to one another, each will perceive the other's clock as ticking more slowly. It's not a trick of perception, not an illusion, but a genuine physical effect woven into the structure of the universe. To understand it, imagine two people. One remains on Earth, while the other travels through space in a high-speed ship, moving close to the speed of light. Both carry perfectly synchronized clocks. For the traveler aboard the ship, everything feels perfectly normal. Their heartbeat, their breathing, their sense of seconds and minutes. But when they eventually return and compare clocks, they discover something extraordinary. Far more time has passed on Earth than for the traveler. The person who stayed behind has aged years, while the traveler has only aged months, weeks, or even days, depending on their speed. This isn't science fiction. It's a direct consequence of the way motion through space affects motion through time. The essential idea behind time dilation is simple yet profound. The faster you move through space, the slower you move through time. When you're at rest, you're moving through time at your maximum possible rate. But as you begin to move, part of your motion through the universe shifts into space, leaving less for time. The faster you go, the more your progress through time slows. This is the universe's way of ensuring that no matter how you move, the total speed through space-time, the combined motion through both space and time, remains perfectly constant. It's important to understand that time dilation doesn't mean time is broken, or that the traveler feels their clock moving slowly. Within their own frame of reference, everything seems normal. Their watch ticks at its usual rhythm, their body functions as always, and they feel no distortion at all. It's only when their motion is compared to someone else's that the difference in time becomes clear. Each person, in their own reality, experiences time as steady and smooth. But when those realities meet, they find that their clocks disagree. This disagreement reveals a stunning truth. Time is not universal. It doesn't tick away identically for everyone, everywhere. Instead, time is personal. Each observer experiences their own flow of time depending on how they move through the cosmos. The faster an object travels relative to someone else, the more slowly its time flows relative to that observer. One of the most intuitive ways to imagine this is through what physicists call a light clock. Picture a simple device with two mirrors facing each other and a beam of light bouncing up and down between them. Each bounce marks one tick of the clock. Now, if the clock is stationary, the light travels straight up and down, short path, short time between ticks. But if the clock is moving sideways, the light has to travel a diagonal path between the mirrors. That diagonal path is longer, so the light takes more time to complete one tick. Yet, because the speed of light never changes, this means the moving clock must tick more slowly than the stationary one. Time itself must slow down to make it work. This slowing of time isn't just theoretical. It's been observed in countless experiments. Scientists have flown atomic clocks on airplanes and compared them to identical clocks left on the ground. When the planes land, the airborne clocks show that slightly less time has passed. The difference is tiny, just billionths of a second, but it's real and measurable. In the world of high-energy physics, the effect is even more dramatic. Subatomic particles called muons, which normally decay in a fraction of a second, can live many times longer when they travel close to the speed of light. Their internal clocks are slowed by their rapid motion, allowing them to survive far longer than they would at rest. What's truly beautiful about time dilation is how it challenges our deepest assumptions about reality. We tend to think of time as a fixed background, something absolute, like a metronome ticking evenly for the whole universe. But relativity tells us that there's no such universal clock. Every object, every observer, carries their own clock, ticking at a rate determined by how they move. And all of those clocks are equally valid. There's no correct time that applies to everyone, only the time each observer experiences in their own frame of reference. This means that time dilation isn't some odd exception. It's a fundamental feature of the universe. Every time you move, however slightly, your experience of time shifts compared to someone else's. We don't notice it in daily life because the effect is microscopic at slow speeds. But the universe is consistent. Whether you're jogging, flying in a jet, or racing at nearly the speed of light, the same rule applies. Your motion through space changes how you move through time. Time dilation reminds us that motion and time are inseparably linked, and that the flow of time is not a single, universal stream, but a vast, shimmering network of countless individual timelines, each one unique, each one real. It's the clearest window into the truth Einstein revealed, that the universe is not built upon absolutes, but upon relationships, and that even something as seemingly constant as time bends gently to the rhythm of motion. To truly grasp why time slows down at high speeds, we need to visualize it, to see, in the mind's eye, how motion can literally reshape time. That's where one of the most elegant thought experiments in all of physics comes in, the light clock. It's a simple, almost childlike idea, but it captures the essence of relativity better than pages of equations ever could. Imagine a device consisting of two mirrors, one above the other, with a single beam of light bouncing back and forth between them. Each bounce, from bottom to top and back again, represents one tick of the clock. This light clock becomes our perfect timekeeper because light always travels at a constant speed, about 300,000 kilometers per second. As long as the clock stays still, the light simply goes straight up and down between the mirrors. Each tick happens after a fixed, predictable interval, a steady, reliable rhythm marking the passage of time. Now, let's see what happens when the clock starts to move. Suppose the clock is placed on a fast-moving spaceship that glides horizontally past an observer standing still. From the perspective of the person inside the ship, the light still appears to bounce vertically, up, down, just as before. Inside their own frame of reference, everything feels normal. The light still takes the same amount of time to travel between the mirrors, and their clock ticks at the same familiar rate. But to the observer watching from the outside, something entirely different is happening. Because the ship is moving sideways while the light is bouncing up and down, the light's actual path is no longer vertical. Instead, it follows a diagonal, zigzag trajectory, up and forward, then down and forward again. From this outside viewpoint, the beam is traveling a longer distance each time it bounces between the mirrors. Yet, and here's the crucial point, the speed of light never changes. It's the same 300,000 kilometers per second for both observers. That constancy of light speed creates a puzzle. If the light in the moving clock must travel a longer distance for each tick, and the speed of light stays the same, then it must take more time for each bounce. The moving clock, therefore, ticks more slowly. The only way for both observers to agree that light always travels at the same speed is if time itself slows down for the moving clock. The spaceship's motion stretches its own passage of time, allowing light to keep its cosmic pace without ever breaking the universal speed limit. This isn't a matter of illusion or trickery. It's the real structure of space-time revealing itself. To the person on the ship, time feels normal because everything in their world, their clock, their heartbeat, even the signals in their brain, slows down together. But compared to the observer at rest, all those processes are happening in slow motion. Time for the traveler genuinely flows at a different rate. The light clock thought experiment captures the entire heart of relativity in one breathtaking image. It shows that the constancy of light speed forces time to stretch and bend in a way that preserves the harmony of the universe. Every moving clock, whether it's made of light, metal, or flesh and bone, must slow down when it moves quickly, because all of them are bound to the same fundamental rule. Light speed is absolute, and time must yield to keep it that way. What makes this idea so powerful is that it's not just a metaphor, it's reality. Scientists have built experiments that essentially recreate the light clock's logic. Atomic clocks flown in high-speed jets or placed in orbit aboard satellites tick more slowly than their twins on Earth, exactly as the thought experiment predicts. The difference is tiny at our human speeds, but undeniable. The faster something moves, the longer each tick of its time becomes. And this simple bouncing beam of light doesn't just explain time dilation, it hints at something far deeper, that every form of motion through space changes our journey through time. The light clock is a window into the fabric of space-time itself, showing that time is not a fixed backdrop, but a flexible dimension that bends in response to motion. When we picture that beam of light tracing a longer diagonal path, we are, in a sense, watching time stretch. Each bounce, each reflection between the mirrors marks the slow heartbeat of a universe that balances motion and time with perfect precision. And this symmetry, that both observers see light move at the same speed even though their clocks disagree, lies at the very core of Einstein's vision. From this simple thought experiment comes one of the most humbling realizations imaginable, that time's flow is not universal. It's personal. It depends entirely on how you move through the cosmos, and the faster you go, the more gently time caresses you, as though the universe itself is stretching the seconds to keep its promise that light will never change its pace. What makes Einstein's vision of time so astonishing, and so different from our everyday intuition, is the perfect symmetry built into it. Time dilation doesn't mean one person's clock is broken or that one observer's reality is somehow more correct than the others. In the world of relativity, both observers are right. Each sees the other's clock running more slowly, and that mutual perception isn't a contradiction. It's a reflection of how the universe truly works when motion becomes relative. Let's return to our two observers, one standing still on Earth, the other gliding past in a spaceship. From the earthbound perspective, the spaceship's clock ticks slowly. Every flash of light between the mirrors takes longer to complete its journey, so time aboard the ship appears stretched out. The Earth observer could watch the travelers' every movement, their blinking, their heartbeat, their speech, all playing out in slow motion. Yet, from the traveler's point of view, it's the Earth that's moving, not the ship. In their frame of reference, the mirrors of their light clock still bounce light straight up and down. Everything aboard feels perfectly normal. But when they look back at Earth, they see its clocks ticking more slowly, its seconds stretched, its people moving sluggishly through time. Both experiences are valid, and both are correct. This is where relativity breaks with the way we're used to thinking. We want to believe there's one true perspective, one real rate at which time flows. But the universe doesn't have a single master clock. There's no hidden hand that decides who's really moving and who's really still. All motion is relative, meaning it depends entirely on the observer's frame of reference. From the Earth's point of view, the ship is moving. From the ship's point of view, the Earth is. There's no privileged observer, no cosmic referee declaring who's right. The laws of physics and the speed of light hold true for everyone, everywhere. This symmetry is what makes relativity so elegant and yet so deeply unsettling. It means that time doesn't belong to anyone exclusively. It bends and stretches according to the perspective from which it's observed. If you and I were moving relative to each other, I would see your clock running slower, and you would see mine doing the same. Neither of us would be wrong, because both perceptions emerge naturally from the geometry of spacetime itself. At first glance, this seems impossible. How can both clocks be slower at the same time? But the key lies in understanding that simultaneity, the idea that two events can happen at the same time, is itself relative. What one observer considers now may not be now for someone else moving differently. This subtle shift in the meaning of simultaneous dissolves what appears to be a contradiction. Each observer measures time and space within their own frame, and those measurements are entirely consistent within that frame. The seeming paradox only arises when we try to compare them from an imagined absolute point of view, something the universe doesn't actually provide. Einstein's insight was that the universe doesn't need a single, shared clock to make sense. The beauty of relativity lies in its self-consistency. The laws of nature, the speed of light, and the flow of time all behave identically no matter who you are or how fast you're moving. This symmetry ensures that physics doesn't play favorites. Whether you're on Earth, on a spaceship, or floating between the stars, the equations governing time and motion are the same. And it's precisely this equality that gives rise to time dilation. When two observers are in uniform motion relative to one another, that is, neither is accelerating, each one sees the other's time as running slow. It's only when one of them changes their motion, by accelerating or decelerating, that the symmetry is broken, as happens in the famous twin paradox, a story we'll explore later. But as long as they move smoothly and steadily past each other, there's no absolute slower or faster flow of time. There are only two equally valid perspectives, each perfectly mirrored in the other. This realization forces us to rethink what reality even means. Time, in Einstein's universe, is not a single thread stretched through space, but a tapestry woven from countless interlocking strands, each representing an observer's unique experience of the world. No single strand dominates. Each contributes equally to the grand design of space-time. The symmetry of time dilation is not a flaw to be corrected or an illusion to be explained away. It's a feature of the universe's deep geometry. It tells us that motion through space and motion through time are inseparably linked, and that the experience of one depends entirely on the other. The universe, it seems, doesn't care about our desire for a fixed frame of reference or a universal now. Instead, it offers us something even more profound, a reality where every viewpoint is valid, every motion is relative, and every clock tells its own authentic story of time's passage. If there's one idea that ties together every strange, beautiful, and mind-bending consequence of Einstein's theory, it's this: everything in relativity depends on motion, but not absolute motion. Time dilation, length contraction, and the warping of spacetime all arise not from how fast something is moving in an absolute sense, because such a thing doesn't even exist, but from how fast it's moving relative to something else. This is one of the deepest shifts Einstein brought to our understanding of the universe, that there is no universal rest frame, no cosmic backdrop against which all motion can be measured. All motion is relative, and so too is the passage of time. To see why this matters, let's revisit our two travelers, one on Earth and the other speeding by in a spaceship. The person on Earth says, "You're moving, so your clock runs slower." But the traveler can just as easily reply, "No, you're the one moving past me, so it's your clock that's running slow." In Einstein's world, both statements are equally valid. There's no special observer who gets to declare once and for all who's truly moving and who's at rest. The laws of physics are perfectly symmetrical, and they look exactly the same no matter where you are or how fast you go, as long as your motion is steady and unaccelerated. This idea stands in stark contrast to how people once viewed the cosmos. Before relativity, scientists believed in a kind of invisible background, an ether, that served as a universal reference point. The ether was supposed to be the substance through which light waves traveled, much like air carries sound. If it existed, then you could, in theory, measure your motion through it and know whether you were truly at rest or in motion. But when physicists tried to detect this ether, they failed completely. The famous Michelson-Morley experiment showed that no matter how the Earth moved through space, the speed of light remained constant. That discovery shattered the idea of absolute motion. Einstein took that result and built something extraordinary out of it. Instead of clinging to the notion of an unseen cosmic stage, he proposed that there is no universal background at all, no ether, no fixed frame, no master clock. The only meaningful measurements are those made between observers. If two people are moving relative to one another, they'll each see the other's time as slowed and distances as shortened, and both are right within their own frames of reference. It's a hard concept to wrap the human mind around because our daily experiences are anchored in seemingly fixed reference points. The ground beneath our feet, the buildings that don't move, the stars that seem stationary in the sky. But even those fixed things are in motion. The Earth spins on its axis, orbits the Sun orbits the Milky Way, and the galaxy itself drifts through an expanding universe. There's no absolute stillness anywhere, only motion relative to something else. If you tried to define a perfect state of rest, you'd quickly realize it's impossible. Everything is moving from some other perspective. In Einstein's framework, time dilation emerges naturally from this relativity of motion. There's no single truth about who is moving and who isn't, only how two observers' motions compare. The effect is entirely relational. If you're on a train speeding smoothly past someone on a platform, you both see the other's clocks running slower, and both are correct in your own frames. The symmetry remains unbroken unless one of you accelerates, turns around, or changes direction, because acceleration introduces a difference that both can agree on. But as long as you're moving uniformly, no one can claim to be truly at rest. This lack of a universal rest frame has profound implications. It means the universe doesn't play favorites. The laws of nature are democratic, treating every observer equally. Time dilation, then, isn't some mysterious effect that happens out there to fast-moving spaceships. It's an inherent part of how the universe ensures fairness between all perspectives. The speed of light stays constant, and time stretches just enough to make sure every observer sees the same physical truths, no matter how fast they're moving relative to one another. And perhaps most fascinating of all, this principle means that the passage of time itself is inseparable from the act of motion. The universe doesn't offer a single, shared timeline flowing independently of everything within it. Instead, it gives each observer their own private thread of time, woven from the fabric of space-time according to their motion. There is no master clock ticking behind the scenes, only countless individual clocks, each keeping perfect time within its own frame of reference. Once you accept that there's no universal rest frame, the strange symmetry of time dilation makes perfect sense. It's not that the universe is playing tricks on us, it's that we've been assuming a kind of absolute background that simply doesn't exist. In reality, all motion is relative, and so is time. The universe is built not on absolutes, but on relationships, between objects, between frames, between experiences. So when we say time slows down at high speeds, we must always ask, relative to what? Because in Einstein's universe, that's the only question that truly matters. There's no absolute motion to define, no cosmic stopwatch ticking in the background. Only you, the universe, and everything else moving alongside you, each with its own clock, each with its own truth, all connected through the unbreakable geometry of space-time. Though Einstein's ideas were revolutionary and, at first, seemed almost impossibly abstract, the beauty of science lies in its ability to test even the most counterintuitive theories against the real world. And over the past century, time dilation, this idea that time slows down for moving objects, hasn't just been accepted. It's been proven again and again through experiments, observations, and technologies that quietly depend on it every single day. One of the most famous confirmations of time dilation came in the 1970s through what's known as the Hafele-Keating experiment. In this groundbreaking test, physicists Joseph Hafele and Richard Keating took 4 extremely precise atomic clocks and flew them around the world, first eastward, then westward, on commercial airplanes. At the same time, identical atomic clocks were kept stationary at the US Naval Observatory. When the flying clocks returned, the scientists compared their readings with the clocks that had stayed on the ground. The results were stunning. The clocks that had been on the airplanes showed a measurable difference in time. Those that flew eastward, moving in the same direction as the Earth's rotation, ticked slightly slower, while those that flew westward ticked slightly faster, exactly as Einstein's theory predicted. The time differences were tiny, just billionths of a second, but they were real, measurable, and precisely matched the equations of relativity. That might sound like an academic curiosity, but the truth is that we live with the consequences of time dilation every single day, quite literally in the palm of our hands. Every time you use a smartphone to navigate with GPS, you're relying on Einstein's theory of relativity to get you where you're going. The satellites that orbit Earth move at speeds of about 14,000 kilometers per hour, and they also sit far above the planet's surface, where gravity is weaker. Both of these factors affect the flow of time. Special relativity, due to their speed, causes their onboard clocks to tick slightly slower than clocks on Earth, while general relativity, due to weaker gravity, causes them to tick slightly faster. The combined result is that time on a GPS satellite moves faster by about 38 microseconds per day compared to time on Earth's surface. That may not sound like much, but if left uncorrected, this difference would cause navigational errors of several kilometers within a single day. To make GPS work, engineers must continuously adjust and synchronize these clocks using Einstein's equations, proving every second that relativity isn't just theory, it's technology. The confirmation of time dilation isn't limited to clocks and satellites. It's also been observed in the realm of high-energy physics, where particles move at speeds unimaginably close to light. One of the clearest examples involves muons, subatomic particles produced when cosmic rays strike the upper atmosphere. At rest, muons decay in a fraction of a second, far too quickly to make it to the Earth's surface. But because they're moving so fast, their internal clocks slow down due to time dilation. To us, their decay appears delayed, allowing many of them to reach detectors at ground level that, according to classical physics, they never should. When scientists create muons in particle accelerators and measure their decay times, they find the same thing. The faster the muons move, the longer they live. Their very existence at Earth's surface is a living proof of time dilation written into the fabric of the cosmos. In particle accelerators like CERN's Large Hadron Collider, where protons and electrons are pushed to speeds within a hair's breadth of light, time dilation becomes not just noticeable, but dominant. These particles, which might exist for less than a billionth of a second when at rest, appear to live thousands of times longer when moving at near light speeds. The machines that study them, detectors, sensors, and complex magnetic rings, all have to be designed with this relativistic stretching of time in mind. Without Einstein's theory, the results would make no sense at all. Even astronauts experience a touch of time dilation. Those aboard the International Space Station, orbiting Earth at over 27,000 kilometers per hour, age just a little bit more slowly than people on the ground. The effect is minuscule, mere milliseconds over an entire 6-month mission, but it's measurable. Their clocks literally tick at a different rate because of their high speed. So, while they float weightlessly above us, they are, in a small but real way, also traveling slightly into our future. These examples together paint an extraordinary picture. What began as a daring idea in Einstein's imagination has become one of the most precisely verified principles in all of physics. Time dilation isn't speculation. It's woven into the functioning of satellites, the design of experiments, and the structure of our understanding of reality. Every clock in motion tells us the same story. Time is not absolute. It stretches and bends with motion, proving that what we experience as steady and unchanging is actually fluid, flexible, and deeply intertwined with space itself. Perhaps the most humbling realization from these experiments is that the universe has no tolerance for human intuition. What feels like an abstract theory from a century ago quietly governs every modern technology that depends on precise timing. Einstein's equations aren't confined to chalkboards or physics textbooks. They're orbiting overhead, ticking inside GPS satellites, streaming data from space probes, and humming away in the deepest corners of particle laboratories. And so, the evidence is overwhelming. Time dilation is not just a strange side effect of high-speed travel. It's a fundamental feature of nature. The faster you move through space, the slower you move through time. And as the experiments show, even the smallest differences in speed can make time itself diverge ever so slightly. From airplanes to satellites to particles blazing through accelerators, the cosmos continually reaffirms Einstein's grand vision, that motion, space, and time are forever linked in a dance that defines the rhythm of the universe itself. Even though time dilation has been proven beyond any doubt, its effects aren't something we can feel or notice in our ordinary lives. Because at the speeds we move, the difference is unbelievably small. Yet, as those speeds climb closer and closer to the speed of light, the stretching of time becomes more than just measurable. It becomes astonishing. To truly appreciate the power of relativity, we need to grasp the scale of how motion reshapes time, from the tiniest fractions of a second to the breathtaking extremes that could separate lifetimes. Let's start small, with something familiar: the speed of a commercial airplane. A typical passenger jet travels at about 900 kilometers per hour, or roughly 250 meters per second. At that speed, Einstein's equations tell us that time dilation exists, but only at a level so tiny it's almost poetic in its subtlety. For someone flying around the world on a jet, time runs slower by only a few nanoseconds compared to someone standing still on Earth. A nanosecond is 1/1000th of a second, so imperceptible that no human could ever sense it, yet our most sensitive atomic clocks can measure it with perfect precision. That's why, in experiments like the Haffel-Keating test, scientists had to use instruments capable of detecting changes smaller than a heartbeat by a factor of 1,000,000,000,000. Now imagine pushing the speed much higher, to that of a satellite orbiting Earth, around 28,000 kilometers per hour. At this velocity, time dilation becomes more noticeable. The clocks aboard GPS satellites, for example, tick faster by about 38 microseconds per day compared to identical clocks on Earth's surface, a difference that might sound insignificant, but would throw GPS navigation off by several kilometers every day if not corrected. This means the satellites are not just orbiting Earth, they're orbiting slightly into the future compared to us. The engineers who designed these systems must constantly adjust for that relativistic time shift, proving that even at moderate speeds, Einstein's theory must be reckoned with. But this tiny effect grows rapidly as speed increases. If you could somehow accelerate to 10% of the speed of light, about 30,000 kilometers per second, time for you would slow down by a few percent compared to someone stationary. A year for you might feel nearly the same, but for an observer back home, just a few extra days might pass. Still small, but now beginning to stretch enough to be meaningful. Push that further though, say to 90% of light speed, and the difference becomes dramatic. At this velocity, your clock would run at less than half the rate of someone's clock on Earth. In other words, while you experience 1 year aboard your high-speed ship, people on Earth would experience more than 2. You could celebrate a single birthday, while your friends back home age twice as quickly. The faster you go, the stronger this effect becomes, and it doesn't increase gradually. It grows exponentially. At 99% of light speed, things get truly surreal. For every year you experience, more than 7 years would pass on Earth. Travel for 5 years from your perspective, and you'd return to find decades have gone by for everyone else. Push closer still, 99.9% of light speed, and time for you slows by a factor of more than 20. 10 years of your journey could correspond to over 2 centuries passing back home. This isn't imagination or science fiction. This is the mathematical and experimentally confirmed reality of relativity. And then, at the threshold of light speed, that ultimate cosmic limit, time stops entirely for the traveler. A beam of light experiences no passage of time between its creation and its arrival, even if it's crossing billions of light years of space. For the photon, emission and absorption happen in the same instant, because from its point of view, there is no interval between them. Of course, no object with mass can reach that speed. Doing so would require infinite energy, but even the mere approach toward light speed pushes time to its knees, slowing it to a crawl relative to everything else. This gradual stretching of time as speed increases paints an extraordinary picture of the universe's balance. At low speeds, walking, driving, flying, the effect is microscopic, almost non-existent. But as velocity rises, time dilation doesn't just become noticeable, it begins to dominate. The universe seems to say, you may move faster through space, but in exchange, you must move slower through time. It's the ultimate cosmic trade-off, a perfect balance between motion and the flow of existence. What makes this all the more profound is that the transition from imperceptible to immense is continuous. There's no sudden boundary, no magical point where time suddenly starts to distort. It's always happening, even when we can't see it. Every airplane, every satellite, every particle in motion is living out a slightly different rhythm of time. The differences only become striking when the speeds are extreme enough for us to notice, when we begin to brush against the upper limits of the universe's speed limit. So when scientists talk about time dilation, they're not just describing a curiosity of physics, they're describing one of the most powerful and consistent phenomena in nature. Whether it's nanoseconds aboard an airplane or centuries at near light speeds, the principle remains the same. As speed increases, time slows down. It's both humbling and awe-inspiring to think about. In the cosmic sense, every motion, no matter how small, changes the rhythm of time itself. You, sitting still right now, are moving through time faster than an astronaut orbiting Earth, and infinitely faster than a particle hurtling through space near light speed. Time, then, is not the great equalizer we once thought it was. It's elastic, fluid, and deeply personal, stretching and contracting, depending on how you move through the universe. And this realization sets the stage for one of the most famous thought experiments in all of physics. One that takes the consequences of time dilation to their emotional and philosophical extreme. The twin paradox, where a journey through space becomes a journey through time itself. The twin paradox is perhaps the most famous, and at first glance most puzzling, illustration of time dilation. It takes the abstract, mathematical idea that time slows down at high speeds and transforms it into something deeply human, almost emotional. It asks a simple yet haunting question. What would happen if two identical twins lived their lives at very different speeds through the universe? Picture this. Two twins, born on the same day, living side by side. One remains on Earth, while the other, let's call them the traveler, boards a spaceship capable of reaching speeds near the speed of light. The traveler bids farewell and sets off on a journey to a distant star system. To the twin on Earth, the ship rockets away, crossing unimaginable distances in what seems like decades. But for the traveler, time flows more slowly aboard the ship. The years feel shorter, the clocks tick slower, and the journey, from their perspective, takes far less time. Eventually, the traveler turns around and heads back home. When the spaceship finally touches down and the hatch opens, the traveler emerges, unchanged from their perspective, maybe a few years older, a little wiser from the adventure. But standing there to greet them is the earthbound twin, now aged decades, perhaps even an entire lifetime. The traveler has effectively leapt into the future. Both began at the same moment in time, but because one twin experienced motion at near light speed, they have lived through fewer moments. Time itself has flowed differently for each of them. At first, this might sound like a contradiction. After all, according to Einstein's principle of relativity, motion is relative. If the traveling twin sees the Earth moving away, shouldn't they also see their twin's clock running slow? Doesn't that mean both should think the other has aged less? This apparent contradiction is what makes it a paradox. But the resolution lies in a subtle detail: acceleration. The principle of relativity applies only to observers moving at constant speeds. In other words, those who are not accelerating. As long as two observers move smoothly past each other, their experiences are symmetrical. Each sees the other's clock running slow, and both are correct. But in the twin paradox, The symmetry is broken the moment the traveling twin turns around. When they decelerate, stop, and then accelerate back toward Earth, they feel the effects of acceleration, forces pressing against them, changes in velocity that the twin on Earth never experiences. That acceleration breaks the perfect symmetry of motion. It's what defines who truly changed reference frames. During this turnaround, the traveler effectively switches from one frame of reference to another. The universe, through the geometry of spacetime, recalculates their relationship to Earth. While the stay-at-home twin remains in a single, consistent frame of reference, the traveler's frame is interrupted, split between the outbound and inbound journeys. This change in frames means that when they reunite, the two no longer agree on how much time has passed. The result is not a paradox at all, but a natural outcome of how space-time behaves when acceleration enters the story. You can think of it like this. In Einstein's universe, each person traces a unique path through space-time, called a world line. The amount of time you experience, your personal passage through time, depends on the shape of that path. The twin who stays on Earth follows a gentle, straight world line through time, barely bending through space. The traveler's world line, on the other hand, swoops and curves, darting far through space and back again. When the two paths meet again at the end of the story, they've traced out different routes through the cosmic fabric, and those routes have different lengths in time. The twin who journeyed through space simply took the shorter path through time. This is not hypothetical. It's been demonstrated in miniature. The same principle that governs the twin story plays out every day in laboratories and in orbit. Astronauts aboard the International Space Station, moving at nearly 8 kilometers per second, age just a tiny bit less than people on Earth. The difference is infinitesimal, milliseconds over 6 months. But it's there, measurable and real. And the faster we go, the larger that difference grows. If we could send a person near the speed of light and bring them back, they could indeed return to find Earth centuries older, while for them, only a few years would have passed. What makes the twin paradox so profound is not just its physics, but its human implications. It transforms relativity from a sterile mathematical theory into something deeply personal, even emotional. It reminds us that time is not a shared experience. It's unique to each of us, shaped by the path we take through the universe. The twin who travels to the stars doesn't just move through space, they move differently through time. They experience a future their sibling will never see and return home as a living embodiment of the relativity of time. It's worth noting, too, that from the traveler's perspective, nothing strange ever happens. Their clock ticks normally, their body ages naturally, and their journey feels consistent. The difference only appears when they return to compare notes. When two different world lines, two different experiences of space-time, finally intersect again. That's when the truth of relativity becomes undeniable. Time is not absolute. It is personal, malleable, and shaped by motion. The twin paradox stands as one of the most vivid demonstrations of this truth, a story where relativity touches human life directly. It's a tale that bridges physics and philosophy, showing us that time is not a river flowing evenly for all, but a vast ocean of currents, each shaped by its own direction and speed. And while we can't yet send humans racing at light speed to test this on a grand scale, the universe itself, through cosmic rays, subatomic particles, and orbiting astronauts, constantly reenacts the twin paradox on its own, whispering the same message across the cosmos. Motion through space always means motion through time, and the faster you go, the less of time's river you experience. When Einstein first unveiled his theories of relativity, few could have imagined that they would someday become a vital part of the technology guiding airplanes, cars, ships, and even our phones. Yet, in one of the most extraordinary fusions of abstract physics and everyday life, time dilation, that subtle warping of time due to motion and gravity, has become essential to the Global Positioning System, GPS. Without relativity, GPS would simply fail. Every map, every navigation app, every automated system that depends on precise timing would slowly drift into inaccuracy until the world's navigation network became useless. To understand why, let's look at how GPS works. A GPS receiver, say in your smartphone, doesn't actually know where it is. Instead, it listens to signals from at least 4 satellites orbiting Earth. Each satellite continually broadcasts the exact time measured by an onboard atomic clock, along with its position in space. Your device compares the time at which it receives each signal to the time it was sent, calculating how long the signal took to travel. Since radio waves move at the speed of light, that time difference tells your device how far away the satellite is. With enough of these distance measurements, your phone can triangulate its precise position anywhere on Earth, within meters, sometimes even centimeters. But here's where Einstein enters the picture. GPS satellites orbit about 20,000 kilometers above Earth's surface, circling the planet at roughly 14,000 kilometers per hour. Because they are moving so fast relative to someone on the ground, special relativity predicts that their clocks should run slower than those on Earth. To an observer down here, the atomic clocks on the satellites tick behind by about 7 microseconds per day, 7 millionths of a second. That might sound negligible, but in GPS terms, that's enormous. Since light travels about 300 meters in 1 microsecond, even a tiny 7 microsecond difference translates into a positional error of over 2 kilometers every single day. If that were the only factor, engineers could simply adjust for it. But nature complicates things further. The satellites are also orbiting high above Earth's surface, where gravity is weaker. According to Einstein's general theory of relativity, weaker gravity means time actually runs faster. So, while special relativity slows the satellite's clocks due to motion, general relativity speeds them up due to altitude. The gravitational effect is even stronger than the motion effect. Instead of 7 microseconds lost per day, the weaker gravity causes the satellite clocks to gain about 45 microseconds per day. When you combine the two effects, the result is a net gain of about 38 microseconds per day for the satellite clocks compared to those on Earth. That means, left uncorrected, the clocks on GPS satellites would get ahead of Earth-based clocks by about 38 millionths of a second every day. It sounds tiny, but when you convert that time difference into distance, since light travels roughly 300,000 kilometers per second, the resulting positional error grows at an astonishing rate. After just a single day, GPS readings would be off by about 10 kilometers. Within a week, your navigation system could think you're in an entirely different city. Within months, it would be utterly useless. To prevent this, GPS engineers do something remarkable. They build relativity directly into the system. The atomic clocks aboard satellites are intentionally adjusted before launch to tick slightly slower on Earth, so that once in orbit, where both motion and gravity take effect, they tick at the same rate as clocks on the ground. In addition, the GPS control systems on Earth constantly monitor and fine-tune the timing of each satellite, ensuring that the signals remain synchronized to within billionths of a second. In short, every time your GPS shows you a location pin, Einstein's equations are quietly humming in the background, making sure your coordinates are right. This blending of theory and technology is one of the most stunning validations of relativity. The effect of time dilation isn't theoretical here, it's practical, measured, and indispensable. The satellite's clocks don't seem to run differently, they do. If engineers were to ignore relativity and rely solely on classical Newtonian physics, GPS would fail catastrophically in less than a day. The fact that it doesn't is one of the most elegant demonstrations of Einstein's genius. What's more, The GPS system proves not only that time dilation exists, but that it's predictable and consistent. Every satellite experiences the same effects, every clock is corrected by the same principles, and every GPS signal across the globe is synchronized by relativistic equations. Even the smallest adjustments, fractions of a microsecond, translate into vast distances when you're dealing with light-speed communication. It's a perfect example of how cosmic laws play out in the most ordinary human activities. Driving to work, hiking in the mountains, or finding a cafe in a new city. The next time you glance at a map on your phone, it's worth remembering that what makes it possible isn't just orbiting satellites and precise engineering. It's a century-old insight that time itself is flexible. Without acknowledging that clocks tick differently in different states of motion and gravity, our world's entire global navigation network would collapse. In a very real sense, GPS is a living monument to relativity. Every ping, every coordinate, every guided route is proof that time dilation is not just real. It's woven into the fabric of the modern world. And while the GPS system is one of humanity's most practical demonstrations of time dilation, the universe offers even grander examples. Far beyond our orbit, in the vast reaches of space, time dilation plays a role in the survival of particles, the aging of cosmic travelers, and even the dance of galaxies themselves. As we move outward into the cosmos, we find that relativity's fingerprints are everywhere, written not just in our technology, but in the very behavior of matter and energy across the universe. When we lift our gaze from the orbiting satellites around Earth and look out into the cosmos, we find that Einstein's revelation about time doesn't just govern our technology, it governs the very heartbeat of the universe. Time dilation, that gentle stretching of moments at high speeds, becomes a cosmic phenomenon on scales so vast and powerful that it shapes the very particles streaming through space. The universe itself becomes a laboratory, proving again and again that time is not absolute. One of the most striking examples of this occurs with cosmic rays, high-energy particles that constantly rain down on Earth from outer space. These particles, often protons or atomic nuclei, are born in violent cosmic events, exploding stars, supernovae, and even the turbulent regions around black holes. As they travel through space, they collide with molecules in Earth's upper atmosphere, creating showers of subatomic particles that cascade downward toward the surface. Among these secondary particles are muons, cousins of the electron, which have an incredibly short lifespan. At rest, a muon decays in just about 2/10,000ths of a second, far too quickly to travel more than a few hundred meters before disappearing. And yet, we detect muons here on Earth, thousands of meters below the atmosphere. They rain down on us continuously, passing harmlessly through our bodies, detected in mountain observatories, underground laboratories, and even at sea level. According to classical physics, this should be impossible. Given their short lifespan and the distance between the upper atmosphere and the ground, muons simply shouldn't have enough time to make the trip before decaying. But they do, and the reason is time dilation. From our perspective on Earth, these muons are moving incredibly fast, more than 99% the speed of light. Because of their enormous velocity, their internal clocks slow down. The processes that govern their decay, the quantum ticking that counts down their lifetime, unfold much more slowly compared to our frame of reference. To us, they appear to live far longer than they would if they were at rest. Instead of lasting only 2/millionths of a second, they seem to survive for 10 or 20 times longer, just enough time to make it all the way to the ground. But what's truly fascinating is that from the muon's point of view, nothing unusual happens. In their own frame of reference, their lifetime is still just a couple of microseconds. It's the distance through the atmosphere that seems different. To the muons, Earth's atmosphere appears contracted, squeezed shorter by the very same relativistic effects. So while we on Earth say, the muons live longer because time slows down for them, the muons would say, the distance we had to travel shrank. Both perspectives are correct, and both are manifestations of the same underlying truth, that time and space are flexible, bending and stretching depending on how fast you move. This cosmic rain of particles provides one of the clearest natural proofs of Einstein's theory. No laboratory manipulation, no human-designed experiment could have planned it more elegantly. The universe itself demonstrates time dilation on a daily basis, showering us with living evidence from the upper atmosphere. Detectors on mountaintops, deep underground, and aboard high-altitude balloons all register the same phenomenon. These fleeting particles persist far longer than they should, because their motion through spacetime bends the flow of time in their favor. The same effect appears in the world's most advanced particle accelerators, where scientists recreate these cosmic conditions under controlled settings. When particles like muons, pions, or kaons are accelerated to speeds approaching light, their lifetimes stretch enormously. Inside massive rings like the Large Hadron Collider or the Fermilab Tevatron, particles that would normally vanish almost instantly can survive thousands of times longer, circling the accelerator countless times before decaying. Engineers and physicists must account for this time dilation precisely. Otherwise, their detectors wouldn't line up with the particle's actual behavior. Every experiment that studies subatomic matter confirms the same story. The faster something moves, the slower time flows for it. On even larger cosmic scales, time dilation reveals itself in the light of distant galaxies and quasars, the brilliant cores of ancient galaxies powered by supermassive black holes. The light emitted from these colossal objects shows variations that, when measured, appear slowed down relative to how we expect them to behave. Astronomers observing supernovae billions of light-years away find that their explosions, which would normally fade in days or weeks, appear to stretch out over longer periods. These time-stretched signals are not because the explosions themselves are happening more slowly, but because the universe's expansion and the relativistic nature of light and motion alter how we experience their passage of time. Even more extreme are the environments near black holes, where gravity becomes so intense that time nearly stops for anything that ventures close. But the foundation for understanding those gravitational time effects, the idea that time itself can slow, stretch, and warp, was built first through the study of motion. The muons above us, the particles in accelerators, and the stars streaking across galaxies are all bound by the same cosmic law. As you move faster, you move more slowly through time. These cosmic examples remind us that relativity isn't just a theory confined to textbooks or laboratories. It's a living, breathing feature of the universe, one that governs not only the grand celestial ballet of galaxies and stars, but also the smallest, most fleeting particles in existence. The very fact that you are reading these words beneath a shower of muons, each one defying classical expectations by surviving its journey through the sky, is a quiet but powerful testament to Einstein's legacy. In the grand scheme of the cosmos, time dilation is everywhere. It shapes the radiation that reaches our planet. It guides the evolution of the universe, and it defines the ultimate limits of speed and aging. Whether in the heart of a distant galaxy or in the space between two mirrors in a thought experiment, the principle remains the same. Motion bends time, and the faster that motion, the greater the bend, until time itself, as we know it, becomes almost still. When we step back and look at everything relativity teaches us, from atomic clocks in airplanes to cosmic rays traveling across galaxies, one breathtaking truth comes into focus. Time isn't universal. It's personal. It's not some cosmic metronome ticking evenly throughout the universe. It's a fluid, living quantity that bends and flexes depending on how you move through space. Every observer, every particle, every beam of light carries its own rhythm, its own clock, and each one ticks at a rate that is perfectly natural within its own frame of reference. There is no single master time shared by all things. Instead, there are countless overlapping experiences of time, each woven into the fabric of space-time itself. This realization is perhaps the most profound conceptual shift that Einstein's theory brought to human understanding. For thousands of years, people assumed that time was absolute, that it flowed uniformly from past to present to future for everyone and everything. Newton himself described time as something that flows equably without relation to anything external. It was thought to be the same everywhere, the same second on Earth as on Jupiter, the same minute for you as for me. It felt natural, intuitive, and true. But Einstein shattered that illusion. He showed that time is not a backdrop, it's part of the stage, and the stage itself bends depending on how you move and where you are. To grasp this concept, imagine that every person carries an invisible clock, ticking away second by second. When you stand still, your clock ticks normally. When you move faster, that clock ticks slower, compared to someone who stays behind. You might not notice it, because from your perspective, your time feels perfectly normal. But someone watching you would see your seconds stretch out. And the reverse is true as well. You'd see their clock moving slower from your perspective. Each of you experiences your own version of reality, and both are equally valid. This means that the passage of time is relative to motion. It's inseparable from how we move through the universe. If two people start together, move differently through space, and then reunite, their clocks will no longer agree. Each has followed a unique path through space-time, and each has lived through a different amount of time. Time dilation, therefore, isn't just a scientific curiosity. It's proof that time is a dimension, not an independent flow. Just as two travelers can take different routes through a landscape and cover different distances, two observers can take different routes through space-time and experience different durations of time. In this view, time becomes something deeply personal. It's not shared in the same way space might seem to be. Your seconds are yours alone, defined by your motion through the universe. The same is true for every atom, every planet, every galaxy. The universe doesn't enforce one rhythm for all. It allows each being to carry its own tempo. This is why physicists sometimes say, each observer carries their own clock. These clocks are not synchronized by any external authority. They're synchronized only within each frame of reference. When those frames interact, when two observers compare clocks after moving differently, the differences in their experiences of time emerge naturally, beautifully, and inevitably. Conceptually, this means there is no single now that everyone shares. The idea that somewhere out in the universe, there's a precise moment that's happening right now, just like this one, simply doesn't exist in Einstein's reality. Your now depends on your motion, your location, and the geometry of space-time around you. Events that seem simultaneous to one person may not be simultaneous to another. Time's order, its rhythm, even its separation from space are not fixed. They're fluid, woven together into one four-dimensional fabric. Once we let go of the idea that time is universal, everything else about relativity falls naturally into place. We begin to see time not as a cosmic ruler that measures everything equally, but as a flexible thread that stretches and contracts depending on how it's used. The faster you move through space, the less of that thread you use for time. The slower you move through space, the more of it you devote to time's passage. The total, your combined motion through space and time, is always constant. You can never move faster than light, because doing so would mean you've run out of thread for time altogether. This understanding transforms our perception of existence itself. It tells us that reality isn't built from absolutes, but from relationships. Time doesn't exist in isolation. It exists in connection to movement, to gravity, to energy, and to observation. It means that the universe doesn't just contain time, it is time, as much as it is space. The two are inseparable. When we move, when we accelerate, when we simply live, we're constantly navigating this interwoven fabric, tracing our own personal path through the continuum of spacetime. And this personal nature of time doesn't diminish its beauty, it enhances it. It means that every heartbeat, every sunrise, every journey unfolds along a unique thread of reality. Two people standing side by side share the same space, but not the exact same time. Their clocks may agree for all practical purposes, but at the most fundamental level, their experiences of time are already diverging. It's only at human scales that those differences are too small to notice. Yet the universe notices. It measures every nanosecond, every stretch, every bend of motion, precisely and consistently. In the grandest sense, Einstein taught us that time isn't something we all share equally. It's something each of us carries within our own frame of existence. It's the measure of how we move through the cosmos, and no two journeys are the same. There is no universal rhythm to life and motion, only a symphony of personal tempos, all harmonized by the same elegant laws of relativity. And when we begin to truly understand that, when we see that time is personal, elastic, and intimately tied to motion, we start to perceive the universe not as a static place of things, but as a living dance of events. Every atom, every planet, every galaxy, and every one of us is tracing its own rhythm in this vast cosmic symphony, where the music of time changes with every step we take through the fabric of space-time. One of the most common misconceptions about time dilation, and one that even popular science fiction often gets wrong, is the idea that time can literally freeze. People sometimes imagine that if you travel fast enough, time around you comes to a halt, or that you could somehow watch the rest of the universe moving in slow motion while you remain frozen in your own moment. But this is not what Einstein's theory actually says. In relativity, time never stops for you. It only appears to slow down relative to someone else's frame of reference. No one, under any circumstances, experiences their own time as frozen or sluggish, because within your own frame, your clock always ticks normally. To understand this clearly, it helps to remember that relativity is all about relationships between observers. Each observer moves through space and time according to their own trajectory, carrying their own personal clock. If you're traveling near the speed of light, you don't feel any change in how time flows. Your heart beats at its usual rhythm, your thoughts form as quickly as ever, and your sense of seconds passing feels just as steady as it always has. There's no distortion from your point of view. Time dilation only becomes apparent when two observers, one moving quickly relative to the other, later compare their experiences. That's when the difference in elapsed time shows up. Think of it like this. Imagine you're on a spaceship traveling close to light speed, and your friend remains on Earth. From your perspective aboard the ship, your time feels completely normal. A second is still a second. But when you look out the window and measure what's happening back on Earth, you'd find that your friend's clock appears to be ticking more slowly. Their seconds seem to stretch longer, and strangely enough, from your friend's point of view, it's your clock that's running slow. Each of you feels your own time flowing naturally, while observing the other's as delayed. This symmetrical perception is the key to understanding why time dilation doesn't mean time actually freezes. There's no universal clock somewhere declaring that real time has stopped for one observer and continued for another. Every observer's experience of time is self-consistent and equally valid. The slowing is not something either one feels internally. It's something each one calculates about the other based on their relative motion. Even at extreme speeds, say 99.999% the speed of light, this remains true. The traveler still experiences the normal passage of time. Their onboard clock keeps ticking, their metabolism functions, their perception continues without change. It's only when they return and compare clocks that the difference becomes dramatic. For them, only a few years might have passed, while for those who stayed behind, decades or even centuries have gone by. To the traveler, everything felt normal the entire time. It's only upon reunion that the true strangeness of relativity reveals itself. This is why physicists describe time dilation not as time freezing, but as time stretching. It's a difference in rate, not an absolute stop. The faster you move relative to someone else, the slower your time passes relative to theirs, but never to the point of stopping entirely, except in the theoretical case of light itself, which experiences no passage of time because it moves at light speed, not below it. For all massive objects, including you, me, planets, and spaceships, time always flows forward within their own frames, just at different rates depending on motion and gravity. Another common misunderstanding comes from thinking that time dilation is somehow a trick of perspective or an illusion, something that only looks slower but isn't real. In truth, it's completely real. When two observers reunite after traveling differently through space-time, their clocks genuinely disagree. The difference isn't a mirage, it's measurable, permanent, and verified through experiments again and again. The reason no one feels it as it happens is because relativity affects everything uniformly. Your body, your thoughts, your heartbeat, your very atoms, all experience the same slowing together. From the inside, everything seems normal. It's like scaling down a film reel. If every single frame is slowed equally, the movie still looks perfectly natural from within. You only notice the change when you compare it to a faster version running elsewhere. Time dilation works the same way. Your movie of life plays just as smoothly, no matter how fast you're moving. It's only when someone watches your reel from another frame that they see it playing in slow motion. This also clears up another misconception, that time dilation somehow means people can pause or jump in time by moving fast. While relativity does allow a traveler to experience less time than someone who remains stationary, it doesn't mean the traveler can ever stop time or reverse it. Time dilation is not time travel in the science fiction sense. It's the geometry of space-time unfolding naturally. You can't freeze time, but you can change how much of it you personally experience compared to someone else. Even in the most extreme scenarios, such as near the event horizon of a black hole, time doesn't stop for the person falling in. To an outside observer, the person seems to slow down endlessly, never quite crossing the horizon. But to the person themselves, time flows normally. They cross the horizon in finite time, feeling no freezing or halting of their experience. Once again, it's the relationship between perspectives that creates the illusion of time stopping, not any internal freezing of time itself. So when we talk about time slowing down at high speeds, we must remember, it's always relative. Time isn't breaking, freezing, or malfunctioning. It's simply adjusting to preserve the deeper symmetries of the universe. Each observer carries their own measure of time, perfectly valid within their frame, perfectly smooth and continuous. The universe doesn't play favorites. It simply allows time to flow differently for everyone, depending on how they move through space-time. This subtle but crucial distinction is what makes relativity so profound. Time dilation isn't about stopping time. It's about revealing that time doesn't belong to everyone equally. It belongs to each of us individually, to our own motion, our own gravity, our own perspective. The universe, it turns out, is fair but not uniform. It gives every traveler their own clock, ticking faithfully along their unique path through space-time. And no matter how fast you go, that clock will never freeze, only slow, gracefully, in harmony with the rhythm of the cosmos. When we pause to reflect on all that relativity reveals, that time can stretch, that space can bend, that motion changes the very texture of reality, it becomes clear that Einstein didn't just revolutionize physics. He reshaped our understanding of the universe itself, and by extension, our place within it. What once seemed absolute, time, space, even simultaneity, turned out to be malleable, responsive, and deeply intertwined. The universe, we discovered, is not a static clockwork machine, but a living fabric, one that twists and curves with motion and mass, one that flexes with energy and gravity. Before Einstein, people imagined the cosmos as a vast, unchanging stage. Space was the floor upon which matter danced, and time was the invisible rhythm that marked every step. The two were separate, eternal, and independent. But relativity merged them into one, space-time, a dynamic, four-dimensional continuum that doesn't merely host events, but participates in them. When a planet moves, it curves space-time around it. When a beam of light passes by, it follows that curvature. And when you move through space, you change how you move through time. Suddenly, the stage itself became part of the play. This revelation forces us to let go of the comforting illusion of permanence. There is no universal now, no single cosmic clock that unites all of existence. Every star, every atom, every consciousness moves along its own river of time, each flowing at a rate determined by its journey through the cosmos. From the viewpoint of relativity, past, present, and future are not fixed boundaries, but fluid regions within the same fabric. What's now for you might already be then for someone moving differently across the universe. This isn't poetic metaphor, it's physical reality. And yet, there's a quiet beauty in that fluidity. Relativity shows us that the universe is not rigid, but graceful, not mechanical, but alive with curvature and rhythm. The very fact that space and time are flexible tells us that reality isn't a cold geometry, but a responsive system. When you move, the cosmos bends around you. When you accelerate, time adjusts to accommodate your motion. Every moment, every movement, subtly reshapes the web of existence. We are not bystanders in this universe. We are participants in its geometry. It also invites a kind of humility. The scales of relativity, the speeds, the distances, the distortions, are far beyond human experience, yet they affect us constantly. They shape the light from distant stars, the ticking of atomic clocks, even the signals that let us navigate our cities. We live inside this flexible universe every second, unaware of how it quietly molds the flow of our lives. To understand relativity, then, is to glimpse something profound, that the structure of reality itself is not fixed and absolute, but relative and relational. Nothing exists in isolation. Everything, from the smallest particle to the largest galaxy, exists only in relation to everything else. Philosophically, this changes everything. It means that our measurements of the universe, time, distance, motion, are not external truths, but agreements between perspectives. It means that reality depends not only on what is, but on how it's observed. The cosmos becomes a grand conversation between energy, matter, and perception, a dynamic dance rather than a frozen tableau. This realization blurs the boundaries between the objective and the experiential. Time, after all, is not just a quantity we measure. It's something we feel. Relativity bridges those two worlds, showing that the physics of the universe and the perception of consciousness are woven from the same continuum. And within that continuum lies an astonishing implication. Motion and time are not separate forces acting upon us. They are us. The atoms in your body are moving through space-time just as the stars are, each tracing its own curved path. The time you experience, your personal now, is a direct reflection of how you move through this vast geometry. Your life is, quite literally, a world line drawn through the fabric of the cosmos, a shimmering path that bends, stretches, and intersects with others in the grand architecture of space-time. Relativity also reminds us that the universe is not built on rigid laws that stand apart from life, but on elegant principles that apply universally. The same equations that describe a photon crossing the void also describe the slowing of time for a satellite orbiting Earth. The same geometry that warps light around a black hole shapes the experience of your own seconds and minutes. In this sense, the cosmos is unified not by stillness or uniformity, but by its consistency, by the fact that its flexibility itself is law. When we think deeply about this, when we truly absorb that time and space are not fixed, that they are living and relative, something shifts inside us. The human sense of certainty gives way to awe. We begin to see that the universe isn't just a place that exists, it's something that becomes. It's constantly evolving, reshaping, and rebalancing itself. Time doesn't flow the same for everyone, yet everything is connected by the same cosmic logic. We are all travelers through this flexible fabric, each of us carrying our own clock, each of us tracing our own rhythm in the symphony of space-time. And that, perhaps, is relativity's greatest gift. It doesn't just teach us about the motion of objects, it teaches us about the motion of existence itself. It reveals a universe that is at once logical and poetic, where precision gives rise to wonder, and where the deepest truths of physics speak directly to the mystery of being. Time and space are not barriers separating us from the universe. They are the threads from which our reality and our very selves are woven. The principle of relativity doesn't only belong to the pages of history or the poetic fabric of space-time. It's the beating heart of modern physics. Every major scientific frontier, every exploration into the universe's most extreme realms, is built on the foundation Einstein laid when he revealed that space and time are flexible. From the tiniest particles inside massive accelerators to the blazing hearts of black holes and the expansion of the cosmos itself, relativity is the invisible scaffolding holding our understanding of reality together. Nowhere is this more evident than in particle accelerators, the colossal machines that push subatomic particles to nearly the speed of light. Inside places like CERN's Large Hadron Collider, LHC, a 27-kilometer ring buried beneath the French-Swiss border, protons are accelerated to such extraordinary velocities that they complete over 11,000 revolutions every second. At those speeds, their time slows dramatically compared to the laboratory frame. If not for relativity, scientists couldn't predict their behavior accurately, nor could they interpret the data that emerges from particle collisions. When these high-energy collisions occur, the particles behave in ways that only make sense through the lens of relativity. Their masses increase effectively due to their enormous energy, and their lifetimes stretch far beyond what classical physics could ever explain. Subatomic particles that should vanish in the blink of an eye survive long enough to leave visible tracks in detectors. Without time dilation, these experiments and the entire field of high-energy physics would be impossible to interpret. Einstein's insights allow us to peek into the most fundamental structures of nature, from the fleeting existence of quarks and gluons to the conditions that shaped the newborn universe itself. But relativity's role doesn't end at the microscopic scale. It also governs the most extreme macroscopic environments imaginable, the places where gravity and motion twist space-time to its limits. The modern study of black holes, for instance, would be unthinkable without relativity. General relativity, Einstein's extension of his earlier theory, predicts that when enough mass is compressed into a small enough volume, space-time curves so sharply that nothing, not even light, can escape. The freezing of time at a black hole's event horizon isn't a metaphor, but a direct manifestation of relativity's principles. To a distant observer, objects falling toward a black hole appear to slow endlessly, their light redshifted into invisibility, while to the object itself, time flows normally right until it crosses the boundary. Modern physicists now study these phenomena not only to understand black holes, but also to test the limits of relativity itself. In the centers of galaxies, where supermassive black holes devour matter and spit out powerful jets of radiation, the curvature of spacetime becomes so extreme that even Einstein's equations strain under the pressure. These regions serve as natural laboratories where we probe the union between relativity and quantum mechanics. Two pillars of physics that, for all their success, still resist perfect reconciliation. The ongoing quest to unify them into a single theory of everything, a framework that would describe both gravity and the quantum world, owes its very existence to relativity's revolution. Relativity also underpins our understanding of the cosmos at large. The expanding universe, first discovered by Edwin Hubble and later explained through Einstein's equations, is itself a relativistic phenomenon. The redshift of distant galaxies, their light stretching as space expands, is an echo of relativity's predictions. The cosmic microwave background radiation, a faint afterglow of the Big Bang, carries imprints of how space-time expanded and cooled over billions of years. Even the accelerating expansion of the universe, attributed to a mysterious force we call dark energy, is described through Einstein's cosmological constant, a term he once considered his greatest blunder, but which now appears to describe one of the universe's most fundamental properties. Our satellites, too, rely on relativity beyond GPS. Telescopes like Hubble, Chandra, and the James Webb Space Telescope constantly account for relativistic effects in their measurements. When they observe distant galaxies, the light they capture has traveled billions of years, light that has been stretched, slowed, and distorted by the warping of space-time along the way. Without correcting for those effects, our entire picture of the universe's past would be blurred and misleading. Relativity doesn't just let us see the cosmos, it shapes the very way we see it. Even cutting-edge fields like quantum field theory and particle cosmology rest on the principles of relativity. The famous equation E equals mc squared isn't just a slogan. It's the bridge between mass and energy that powers everything from nuclear reactors to the fusion processes inside stars. Without it, we couldn't explain how the sun shines, how elements are forged in supernovae, or how energy transforms into matter in the early universe. Relativity is the silent architect behind the cosmic story itself, the translator between motion and time, mass and energy, gravity and light. And as our technology advances, relativity's relevance only grows. In the coming decades, as humanity builds faster spacecraft, more precise atomic clocks, and more powerful observatories, we'll need Einstein's equations more than ever. Interstellar travel, gravitational wave astronomy, and even quantum communication across vast distances all depend on our understanding of spacetime. Already, instruments like LIGO and Virgo detect ripples in spacetime, gravitational waves, caused by the collisions of black holes and neutron stars billions of light-years away. These waves are the literal vibrations of Einstein's spacetime fabric, detected here on Earth with precision so fine it can measure changes smaller than a proton's width. Relativity has moved far beyond the realm of abstract thought experiments. It's become a tool, a compass that guides humanity as we explore both the smallest particles and the largest structures in existence. It shows us that everything, from the behavior of a single atom to the expansion of the universe is governed by the same elegant set of principles. What's extraordinary is how seamlessly these ideas blend science and philosophy. Relativity doesn't just describe how the universe works. It reveals what the universe is, a dynamic interplay of energy, matter, space, and time, all linked by the geometry of reality itself. Each discovery in modern physics, every particle detected, every black hole imaged, every cosmic signal decoded, is a verse in the poem Einstein began more than a century ago. And yet, even as relativity helps us build technologies, peer into black holes, and trace the universe's history, it also reminds us of something timeless, that our understanding, no matter how advanced, is always evolving. Space and time, far from being rigid or final, are as alive and responsive as the questions we ask about them. The more we explore, the more we find that relativity is not a limit to our curiosity, but an open invitation to look deeper, think wider, and remember that reality itself is far stranger and far more beautiful than it first appears. At the heart of everything we've explored lies a single, elegant truth. Time slows down at high speeds because the universe insists on preserving the constancy of light. No matter how fast you move, no matter where you are, the speed of light remains the same. And to make that possible, time and space must bend and stretch in perfect harmony. This balance is not a flaw or a trick of perception. It's the very structure of reality. Motion, space, and time are not separate ingredients of the cosmos. They are threads of the same fabric, woven so tightly together that changing one inevitably reshapes the others. When you move faster through space, the universe gently slows your movement through time, maintaining its cosmic equilibrium. This simple yet profound principle explains everything from the ticking of atomic clocks on airplanes to the aging of astronauts, the survival of cosmic particles, and the curvature of light near black holes. It's a universal rule, one that governs the smallest particles and the largest galaxies alike. Einstein showed us that we don't live in space and time. We live within space-time, a single, unified continuum. And in that continuum, every motion alters the rhythm of time itself. It means that time is not absolute, but personal, shaped by your journey through the cosmos. Every second you live is a reflection of how you move through this grand geometry, a geometry that flexes, curves, and dances to preserve the universe's one sacred constant, the speed of light. So, when we say that time slows down at high speeds, what we're really saying is that the universe keeps its harmony intact. To protect light's constancy, it transforms space and time into two sides of the same coin. In doing so, it reveals a breathtaking truth, that reality itself is not rigid, but alive with connection. We are all travelers in this fabric, our paths through space shaping our passage through time. And in that dance of motion and light, the universe reminds us of its deepest secret. Everything is connected: motion, space, time, and existence itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.